recording. So yeah, right now it's just us, so we can work on any particular section you want to. So if you have any like a specific lesson you wanted to go over, we can totally do that. Or like if you had your own problem that you wanted to do, that works as well. Just let me know and we can do whatever. And if more people start joining, then I'll transition into the prepared thing where I was gonna go through each lesson, do like one or two problems from each lesson just to do an overview. But when it's just us, and even if there's like one other person here, I'll just ask you guys specific questions and we can do that, because I feel like that'd be more effective use.
Okay, can you hear me?
Yes, I can.
Oh, texting. I think I've got the derivatives down. I'm looking back on my notes to see what.
Yeah, no worries. Take your time.
I think I'm getting the derivatives velocity be considered A, I guess you can call it.
Okay.
So next up, I really haven't started reviewing yet. Rigid body.
Sure, we can do some rigid body. Did you have a preference from 1 to 4? Or do you want to just start with 1 and work our way to 4?
Probably start with 1.
Okay. We do.
I haven't looked at it since lecture.
No problem. We do have James joining us here for our rigid body. I think he's connecting. Yeah, he should be in here. All right. Welcome to Quiz 5 Review, James. It's just you, me, and Kat right now. We're going to start with some rigid body stuff. And if you have any questions along the way, just let me know. You can say anything through the mic or type in the chat. Either one works for me. And if either of you see somebody join in the waiting room and I don't notice them, feel free to let me know.
Okay.
Okay, I'm just getting problem pulled up.
Which problem are we going to start with? Is it one on the canvas?
Yeah, we're starting with rigid body kinematics 1, problem 1. Yeah, this works. So just make sure the camera's good. Yeah. All right. So starting with rigid body kinematics 1, problem 1, we have classify, or well, the problem is a Ferris wheel, and it wants us to, at a particular point, determine the tangential and normal components of the acceleration at a specific point. So first thing we want to do is I'm going to go ahead and draw the Ferris wheel. You guys won't have to on the quiz because you're provided with the diagram, of course. So we'll go ahead. I'll go ahead and draw it on this side.
Okay.
Just so that it's over here. This is a circle. Pretend it's not like this weird egg shape. Okay, where we have this specific point here, B, and they give us the distances here and here. 5 feet. And let's just close this pop-up. Oh my God, stop popping up. Okay. And they tell us that the radius is 20 feet. So this problem wants us to find the tangential and normal velocity, or acceleration, I should say, at this point on the Ferris wheel. And we are given that at point A, which is on the outer radius, that the acceleration here, so acceleration at A, is equal to minus 80I minus 60J. And this is in feet per second squared. And we know that the Ferris wheel is rotating counterclockwise about the center. So I'm just gonna indicate that with this arrow. And yeah, that's everything we're given. So in order to get to this point, we don't really know the acceleration here. We need to find some more information by using a rafa stick from O to A, because that will allow us to solve for the omega and alpha values and then transition those to a rafa stick from O to B. So starting with that, we'll have our fixed end A, our fixed end O, all the way out to A. This is O, and here we have A, where we have minus 80I and minus 60J for acceleration. So I is going to be our X and J is going to be our Y. So we're going to have 60 down. This is 60 frames per second, or feet per second squared, and 80 feet per second squared. And if at any point something is too small or there's a glare or something, feel free to let me know and I will adjust where I'm writing or the camera or however I can fix it. And so in addition to this, we also have the alpha and omega values, which we will just throw on here. Alpha OA and omega OA. And we know the radius here. It's just this 20 feet. So R equals 20 feet. So from this information here, we can go ahead and solve for our omega by saying that AN is equal to omega squared times R. And this is just a general formula that you can use for all rafa sticks. AN, which is 80 feet per second here, 80 feet per second squared, is equal to omega squared times R. Since we know AN and we know R, we can solve for omega. You plug in minus 80 for AN and you plug in 20 feet for R. We get that omega is equal to 2 RPS. And then we can take the tangential acceleration, which is our 60 here. We can say AT is equal to alpha times R. We know our AT, we know our R, so alpha has to be 3 RPS squared.
And from memory, our omega and stuff, those are body. So those apply to B2, right?
Exactly. So these same values are true everywhere along this like rotational center. So at every point on this Ferris wheel here, like literally anywhere, you could draw any point you wanted to, etc. These values will hold true, and you can use a different radius to solve for your AN and your AT at literally any point you want in the circle, if you know these. Which is exactly how we're going to go about doing this. Since we know omega and alpha, we can go ahead and move our rafa stick from O to B. I'm going to draw it again here. Here we have our fixed end O, all the way out to B, like this, where we know omega and alpha. So we have 2 RPS and 3 RPS squared. But now we just have AT and AN.
Can I ask a quick question just for my memory's sake?
Yeah, absolutely.
The alpha is always in the same direction as the atangential, right?
I believe so. That's the way that he writes it on the solutions. So I think that's a good thing to follow. Every solution I remember seeing shows that pattern, that alpha goes with AT.
Okay.
And I wrote it alpha going this way because you can see like in this one, alpha's going that way. So this is the same direction as that. It's all clockwise. And AT is going this way. AT is going this way, like about the circle.
Okay.
So coming back to our AN and AT equations, we can just write AN is equal to W squared R. We have W, we have R, which the R for here, we know because we can say 5 feet and 12 feet. So we can solve for this radius by doing Pythagorean theorem. Hey, what's up? Good, we're just starting with some rigid body stuff. This is the first lesson for rigid body. Okay. Yeah, so you really haven't missed much yet. Okay, perfect. Okay, so we'll solve for the radius of this raffle stick by doing Pythagorean theorem with these. So the radius here comes out to be 13. I'm just gonna write 13 feet here. So we have our omega value as 2, our radius as 13. So our AN at B comes out to be 52. Yes, it's recording, yeah. 52 feet per second squared. We come down with AT equal to alpha R. We have alpha from before and our new R value. So we can go ahead and say AT is equal to 39. Yeah, 39 feet per second squared. And this would be your final answer. So just to recap for you, since you came in when we were right about here, this problem wanted us to find AN and AT at B. And so we had information for A. Should label this as A. So we used the rafa stick of A to solve for our omega and alpha values, which we get here by using the given AN and AT from this expression. I component is always your AN. Well, I guess I component is your X and J is your Y. So it happens to work out because this is a horizontal raphistic. So that's how we say that this is AT, because it's the y component going down and I is the x going left. That's how we get these by using our A and AT equations. We transition these values into the next raphistic for B, and to solve for this radius using our previously found alpha and omega, and the new radius, we can find our new AN and AT. So any questions on that?
No, I don't think so.
Okay, any questions in Zoom?
No, that wasn't horrible.
Okay, cool. Yeah, so this concept is kind of like, basically like this exact thing is how all the rest of the sections for particle kinematics, or for rigid body kinematics, they're all based on this. And it's just like bigger versions of this and like more raphistics going on at one time. So if you can remember like the fundamentals of, yeah, this is the fixed point and we transfer the values from here to here, then it's not too bad. Okay, so that was the first section. You can go ahead and move to rigid body kinematics 2.
And this will be uploaded.
Yeah, I'm fairly confident I'm recording. Yeah, I am.
Okay. Class of 3.
Oh, no worries, man. Yeah, I'll have the recording up as fast as I can after I finish here. Okay, this is a good one. So let's do rigid body kinematics problem 2. Yeah, rigid body kinematics 2, problem 2. So here we have a structure that looks like come on, marker. There we go. Like this. Would this being, sometimes it's hard to see the labels. This is point C. There we go. Is this on screen? Can you guys see this?
Yes.
Okay, cool. So we are given, this is B. Here we have A. And we're given that omega BC is equal to 2 radians per second. And we're given that this is a 3/4, given that this is 6 inches, this is 4 inches, and this is a 3/4 the other way. So it wants us to, at the instant shown, the angular velocity of BC is, so it gives us this, and wheel A is rolling, and it's a no-slip wheel. So this wheel is no-slip. And classify the motion of each rigid body in the figure and determine the angular velocity of wheel A. So classifying the motion of each portion of the figure, we can go ahead and say that BC is a raphistic. We know that BC is a raphistic because it has a fixed point right here and rotates about that fixed point. And then we would say that AB is a GPM, because as you can see, neither one of these are fixed and it kind of just moves independently. And we would also say that wheel A is GPM for similar reasons. It's not fixed anywhere, it moves on its own. So we've done the first part of the equation already, or the first part of the problem already, classifying the motion. So now we just need to determine the angular velocity in wheel A. So what we want to do is establish our velocity equations. We know here in the center, B is VB. And from here, we can say that VB is equal to VC, or yeah, we can say that's equal to VC plus V of B relative to C. And you can always say that this is true. You can say that velocity of a point is equal to the opposite end of the member plus the initial relative to the other one. And we also have the other side of B down at A. We have equal to VA plus VB relative to A. And this is going to be the equation that will eventually allow us to solve for what we're looking for. So replacing this equation with the kinematic diagrams that we have, we can say right away, VA, velocity of A, is going to be something like this. And we're just going to label it as VA. Then we have plus B relative to A, and that's going to be represented by a raffle stick. Because it's relative motion, we're assuming that A is the fixed point here. It's going to look like this, where we have omega AB and an unknown velocity here. And this is going to be equal to the left side that we have, where we say that VC is 0. This is fixed. So VC is going to be 0. That's plus B relative to C. Just like this side, we're going to have a raffle stick. Where we know this omega value. Because it is given to us, and then this velocity here. So this would be how you would draw out these diagrams. Are you good? Okay. Any questions in the Zoom about these diagrams?
I think I understand it.
Okay, cool. So the next thing we want to do is do some of the forces in the X, some of the forces in the Y. So we'll start with X, some of the forces in the X, and for this, they say that left is positive for whatever reason. So right away, we're gonna have 0, and then an X component of this member. So we would say V BC times 3/5, because 3/4, it's a 3/4/5 triangle. This would be equal to VA plus the X component of this, which is going to be VBA times 4/5. And so this would be our initial equation. We're going to replace some of these velocities with omega and radius values so that we can get stuff to go away. So then we have our sum of forces Y, 0 for VC, and then VBC, 4/5 is equal to 0 for VA. So then we just have VBA is 3/5. So now that we have these equations, we can replace VB, we can replace VBC here with omega times the radius, because we know that the velocity is equal to omega r here. Which is going to give us that VBC is equal to 2 radians per second times 6 inches. So VBC VBC, they say it was 12 inches per second IPS.
Stupid question for you.
Yeah, go ahead.
The velocity equals omega r is for all problems, right?
Yes, this is a formula that you can use for any rapid stick. Anytime. Yeah, just go ahead.
I said thank you.
Oh, okay, you're welcome. Yes, so once we get our value for VBC, we can replace with 12 IPS. And so now we only have one unknown here, which we can use this equation and say that VBA is going to be equal to, the font's just so small in the solution. I always want to make sure I'm writing the correct number down. Yeah, they say that VBA is equal to 9 inches per second. And that's just because we substitute the value that we find for VBC into our Y equation, and VBA is the only one left. So once we know that, we can put in VBA here. And now we only have one unknown here. And we can say that VA is equal to is equal to 4.2 IPS. Yes. And that's just from substituting here and substituting here. I believe that is what to determine the angular velocity of wheel A. So
VBA.
say
I
again?
got 16 for VBA. Sorry, 12 times 4 divided by 5 divided by 3 divided by 5, right? I got 16.
That would make sense.
That's okay. I was just making sure I'm not doing anything wrong. Yeah.
No, it's totally possible that I mixed something up. Let me just see. So they go through, they say VA plus 3/5 VBA. Or what? It's because this is supposed to say 3. Wait, no. In the X direction? this one should be 4, yeah. Why does he have 3 here? Either I honestly think that that's just a mistake in the solution, because he very clearly labels the raphastic the same way that I did, with it being 3, 4, and 3, 4. But then he does like for x direction of BA, he says 3/5 instead of 4/5. But he has it labeled like this in his solution. So I assume that that's a mistake in the solution.
Okay, as long as I'm not screwing up.
Oh no, you know what it is? It's because, see, this is actually a good thing that we're not talking about this. So when you draw your raphastic, right? And this is why I should have labeled it here as well. This is the raphastic for BC. So this is 3, 4. But our velocity values are not this raphastic. Our velocity values are here. It's 3 and 4 like this, because the velocity vector is perpendicular to our raphastic. That's how he gets the proportions that he does, where this is 3, this is 4. But he says 4 and 3 like this.
So they reverse in the velocities?
Yes, so the velocities have a reversed proportion in this triangle than the raphastic. So I will draw a larger scale of it. So if you have any raphastic, right, and say this is 3 and 4, velocity vector here is 4 and 3. And this is very important. So that's how our values are messed up.
It's perpendicular to the raphastic.
Yes, because it's perpendicular to the raphastic. So this triangle gets flipped onto the vector. So our VBC is still correct. So we come down, we substitute that here. And this is supposed to be 4, and this one is supposed to be 3. And this one is supposed to be 4, and this one is supposed to be 3. I think. Y for this one should be 3, and Y for BA should be 4. Is that how he has it? Yes, it is. Okay, awesome.
That makes sense.
So it was 12 inches a second, or BA 4.2, IPS the correct answer. So
Right, yes. So VBA should come out to be what we had it as. VB we're just dividing 4.2 by 1. And this would be the final.
What is the question asked for again? Just which is
Yes, which is this omega of the.
okay. Thank you.
I'm getting another problem pulled up. Whenever the problem wants to load, we can move on. In dynamics, but by the time you're doing the more advanced stuff, you up for the next several civil courses. This problem is still so after work energy, you guys only have impulse momentum, and then it's the final. you guys had taken quiz 5 last Friday, like it was originally planned. I could maybe see one more. Wow, my internet connection is terrible today, I guess.
Why?
I hit you up. I was like, what about
Okay, here we go. Nice. So rigid body kinematics 2, problem 4. We have, again, a no-slip wheel with 2 members attached with 1 fixed point. They give us the angular velocity and angular acceleration of one of the members. And it wants us to determine the angular velocity and acceleration of one bar and the other bar. Oh, they give us the omega of the wheel we know that this is 30 degrees and meters. Then once again, we'll move into our C relative to B, relative to D. So taking these equations and drawing our, we can go ahead and start with VB, where we're going to have and we have VC D as a fixed point, making this a rapid stick. Where our VCD is here. No slip wheel. We know that this point of contact and the center of the wheel makes a raffle stick from of B right away by doing our omega times 2. Hey, what's up? So our velocity of the, so VB is going to be equal to our omega value, 6 RPS. Times the radius of the wheel, omega R, we can solve. So that's how we get the 12 centimeters per second.
Thank you.
12 centimeters per second. And here, leave this out. So now that we've established that, we can go ahead and say it's equal to, we're gonna have minus 12 centimeters per second. Then we need the x component of VCB. So we get the x component of this if we for so therefore, if this angle is 30 degrees, we know that this angle is 30 degrees. This whole thing has to be 90, 30 degrees. So is here, then this has to be 60. And if that's 60, these lines are parallel. $60 degrees. So we have our first equation with two unknowns. Times sine 60 degrees. So with two equations and two unknowns, you can solve this as a systems of equations, or like if you know how to put it into your calculator as a matrix, you can do it that way as well. But feel free to solve it kind of running out of space. They end up saying that VCB is equal to they skip the step of they substitute their velocity values right away with the radius times the omega. Piece being 8 5. Any questions? They create the equations exactly like we did, and then they say V is equal to omega R. This equation comes up again for each of these V values and for R, which is where we get the VCD is equal to 8 omega. I didn't or put the 8 omega next to it, but they do the same thing for here. So the way they write it is like this.
I guess I'm gonna have to review it on my own.
I mean, it just a little bit. So how we set up does the initial
Review. Then I no, I just it's just not clicking in my head. I don't getting it.
okay, so when we initially set up these equations for the forces in the X and Y, right? Do these diagrams make sense?
Yeah.
Okay, so once we have the diagrams, we need some of the forces in the X direction, right? So in this first diagram, all 12 is going perfectly to the left. So that's why we say minus 12. Then in the second diagram, we have our velocity here going down and to the right. So we need our X component of that. So we say plus V CB.
I get all of that. I just don't get.
Oh, okay. Sorry, that's my bad. I misunderstood the kind of question you were asking. So once you substitute these values, all you have to do is
Um. Isolated. And then you're plugging.
yeah. And multiplying, dividing, everything that you need to do, and you should only have one unknown in this equation and you, okay. So that was the angular velocity. The problem also wants us to find the angular acceleration as well as the acceleration of point C. Because I'm going to leave these written here. I'm going to go ahead. We just set up to solve for our angular acceleration. So acceleration of C, excuse me, is equal to acceleration of B plus acceleration of B relative to C, which is equal to acceleration of C. Wait. Yeah, I wrote this backwards here. C relative to B and C relative to D. So just like we set up the velocity, from there we can draw our acceleration diagrams where we're given, I wrote that here. A, B is equal to alpha of the wheel times the radius, which is 2. So that means alpha B is equal to and represent that just with a diagram like this. We'll have our C relative. We have our B our omega CB value of 2.09. So we can throw that a second. We have unknown know that because this is 4,3, where AN we can say right away, because we know one equation that we do know, that AN is equal to they don't write the value, so I'm just gonna well, do I have a calculator on hand? Okay, so 10.45. And again, this just comes from omega squared times r. So then, and so this would be equal to a d, which acceleration at d is going to be 0 because it's a fixed point. And then finally, we would have we would have our raffle stick for c relative to d, where we assume d is a fixed point. Draw our stick. We know that the omega of this point is 0.907. And it also has an unknown alpha along with the same AT and AN setup times 8. For 7.256 centimeters per second squared. Wait. No, it's omega squared. Whatever. 5 times 2.09 squared. There we go. Sorry, this changes just because I forgot where we know that in general, I'm gonna write this here, AN is equal to is equal second squared. That's gonna be plus the x component of our AN. So this will be the 21.84. I'm just gonna label it as AN for the sake of space. X component, so we use 3 over 5. And that would be minus because our AN is going down into the left. AT will say plus. I'm going to label these as AN and AT1, and these as 2. And that's going to be equal to nothing for AD because of AN and AT here. So if we know this is 30 degrees, like we said before, this must be 30 degree angle here is 60 degrees because this angle is 60 degrees and then angles must be the same. And we know $60 degrees. That's going to be minus because we can see it's going left. And then we'll have plus for our AN because it's going down and right. Show these are known. Our only unknowns here are ATs. Then we can do our Y component. This has no Y component. So we can go right to this piece. We can say our 3/5 of AT1. And this is minus because it's going down is equal to nothing one for AN2. And being right here and 30 degrees being here. And yes. So this would be your entire Y equation. Once again, our AN values are known. We know that normal acceleration in the first part of the problem. Knowns are AT values. Here, these are the same, and these are the same. So before, you would isolate one variable and substitute what you get into forms of equations. And you could replace your ATs. I'm going to. So our AT with alpha BC times the radius. Do that again over here. And then our AT2 is 8 centimeters. There we go. .25 radians per second. The question was asking for us to find the velocities and the angular velocities and angular accelerations of both of these members, which we this instant. So once we have these values, acceleration at c is equal to, we can either use AB plus c relative to b, or we can use AD plus c relative to d. I'm going to go ahead and make some space. Plus A C D. We know this is 0, so I'm just going to do that. And then our diagram of AC. The unknown pieces that we have of it will have AC Y component. This is going to be equal to the drawing we had for so is going to be what we had over there, 6.58 centimeters. So knowing that, we can do what we did for this, we would have an x component equation where we have AC x is going to be equal to the x component of both of these. Which we know from over there is going to be our AN times cos 60 degrees, because ACX, we have all the components we need to know. So we go ahead and say that ACX is equal to 8.10 centimeters squared to the left. And we say left because this answer comes out negative, and our assumed direction of AC being to the right must be opposite. So we say to the left. We then equal to the y components of these, 6.58. This is negative. This is negative. Because these are both going down. So our final magnitude of AC is equal to the square root of the x component squared plus the y component squared. And this would come out. So in order to get the direction, we can do tangent of a theta that's unknown is equal to, if tangent is the angle of the magnitude, we can represent that with something like this. We know that both of these left and down. So we can say tangent is opposite. So it might be easier to draw it like this. Yeah. So this theta, opposite y component over adjacent x component is going to be equal to our magnitude, a 27.193 divided by 8.1. So doing inverse tangent of this quantity gets us that theta is equal to 73.4 degrees. And so the final answer for the acceleration of C would be saying that and so this answer for this problem. This was a really long one to get here. Any questions on this? No? No? Okay. And like I said, this is recorded, so if at any point you want to go back and rewatch if something was unclear, you totally can. I'll have the recording going or after the review's over. Oops. Okay, so here we have rigid body kinematics 3, problem 1. This problem gives us a structure of members that has a angular velocity of 4 radians per second counterclockwise, and it wants us to determine angular acceleration in bar CD. So very similar to what we've been doing so far. We have the initial bar, and bar BC, and bar CD. So we have something that looks like this. And we're given omega AB as 4 radians per second. So starting with relative acceleration equations, because it wants us to find, we'll start here with our point acceleration B. The acceleration of B relative to C. So B relative to A, we can represent as a raffle stick. I should draw it the correct way. Something like that. And we have omega equals 4. It's going to be here, AN always like this. If this is constant, that means our alpha value, your alpha has to be 0. So we have a R. These are the important equations, basically. So we can say, knowing our omega value, we can say that our AN is equal to, this is 8 So I never get this back to you. Oh, thank you.
Want to be here for the rest of the remainder of the time.
Okay. Cool. So our right. Okay. So we represent AC with the raffle stick of D to C, just like we can at any other point. So we'll say AC. So raffle stick like this point being D, and here we have C with so hard to read this sometimes. They tell us is equal to 3 RPS. So this is all given. So coming back here, we have our omega I wrote this the wrong way too. The omega, and we have the radius. So that's going to be omega squared. 3 squared is 9 times the radius. Here is 10 inches per second squared. So here we have, this is 0. Here we have B relative, that C is a fixed point, and that we have our B coming out like this. So we have five RPS or AN. Once again, and we can know the AN by doing 5 squared times the radius, which we know is 10. So this AN is going to be 250 inches per second squared. Sure.
From the picture. So on that side, it's going this way. So on that one. It's not.
You mean right here?
Why is that like? Yeah. Opposite of that one?
But the given value for omega BC is 5 radians per second. This, right?
Yeah.
Even though this is technically clockwise, you would want it to be relative to your fixed portion. So you would draw it like, but this is the more correct way. So now that we have all 3 of these diagrams set up, we can go ahead and say some of the forces X is going to be equal to AT. These are all going to be 1. These are all going to be 2. And these, so here we have the AT components for this last piece. So for the last piece fourths. Writing this on your rapid stick, we have some is 4 going up and 3 to the side, so that's going to be 3/5. And then we have our AN going to the right as well, so that's going to be plus 250 inches per second squared times 4/5. And that is the exact setup we need. So we have our first equation with 2 unknowns, AT2 and AT3. Second equation, some of the forces on the Y, we're going to have AT1, except if we know that the angular acceleration here is 0, because like we said at the beginning, AT is alpha times R, AT is 0 as well. So we're going to have 0 minus 90 and then the y components of our third diagram. So the third diagram has AT3 going up, and then a N3, which is the 250, going down. And then we have this equation with only one unknown, but since the equation specifically asks for angular acceleration, we can go ahead and replace our ATs with alpha R's. Alpha T3 with the same thing. We replace acceleration of T2. Radians per second squared. Taking that and substituting it in here, variable. And we get alpha CD is equal to have one or several graphistics or general planar motion members that you can either, and if you're doing velocity, you have velocity on the end, or if you're doing acceleration, you have AT and AN on the end. You set them up to be equal to each other, X and Y, boom, solve for what you need. And this general process, applying it it's applying it to different shapes and recognizing that the path to have a drink and rest my voice. I've been talking for the last like 2 hours
like go like, I don't know, if they're demos, yeah. That's like the top and I go down. So yeah, it's weird as shit. Make it easier, so. Yeah, it's kind of my brain hurts now.
All right. Let's go ahead and jump into rigid body kinematics 4. The wheel moving forward, and we can represent this ICZV by showing that this wheel at the point of contact becomes a raffle stick at the center. And it has its omega value here. And it has a velocity here. And at this point, the same omega value would apply. So at any point on the wheel, I could pick right here. I can go from this point of contact, ICZV equals ICZV. Then idea for finding your ICZV is you want to draw, oops, you want to draw your velocity vector like this that are moving. These 2 points do not move, they do not get velocity vectors. And then through the same point, you want to draw a perpendicular velocity where you would draw a line like this. And for this velocity, where these 2 lines cross right here is your IC, no matter what shape. So we could have some like random thing like this very similar to the problem we just did, where this is going to, I don't know, let's say go like this. This is going to go like this, dotted line. These, find your velocities, draw your perpendicular lines, and where they intersect is your ICZs. And then finally, the last example I wanted to show for this, except instead of another raffle stick at the end, we have something like a slider. So imagine this uh, and a situation like this. So knowing how to find our ICZBs, let's jump into a problem. For problem 3. Wants us to determine the angular velocity of links B, C, and CD at the instant shown. So I'll go ahead and draw this for us. This everything they give us, I think so. Oh, and they give us omega AB or BC and CD. So what we're looking for is alpha BC and alpha CD. These are the things we're looking for. So what we can do using ICZV is here is a velocity vector, and here is a velocity vector, this one being about this fixed point and this one being about this fixed point, straight through the title, and find our ICZV right there. And once we have that, we can set up to solve for the total height from C to the ICZV. I'm gonna go ahead So we can set up a situation to solve for this total distance. And just as a note, this is also. So we can say that tangent theta, the theta being the 30 degrees here, and if tangent is the ICZV, this is equal to the unknown y over 0.4 meters.
Oh, yeah. Well, those are exactly the same.
So it's 0.031 meters. Members here. And we can start off with VB. We can say VB. This is going to be equal to omega AB, which is known as 10, times the radius
Why isn't the individual squared?
because it's only squared in your acceleration formulas. Yeah, so we know so then going off of AB and moving on to BC, we can say VB is equal to omega BC with Pythagorean theorem. So they say 0.4 squared times 0.231 squared, and then square root that.
You have gone to breakfast? Yeah, I mean, I guess it's not only.
So 0.619 yeah, 0.4. this distance from B. And we can use that as our radius here. Radians per second. To omega BC radius times the radius from C to here, which is why we have this height. So VC radians per second. So which we did of BC and CD, this member and this member. So, and then you use your V equals omega R equations to transfer. Any questions on that?
Oh, no.
Well, dang, okay. That's all 4 sections of rigid body. Do you guys want to do particle or particle? Okay.
Something from particle kinematics part 2. Like, I don't care.
Yeah, for sure. We can do that for sure. Head out. Thanks for everything. No problem. Thanks for coming, man. Will it load quickly or slowly? Probably slowly. Oh, quickly. Never mind.
Yeah, we didn't think it in. We got to put on.
Good question to do. 3. And you'll probably, I think you guys do all these problems in class, in the face-to-face. Going to get to. And it's an important question to know how to do. So this problem is kind of a strange one. And it is represented by a road. There we go. Like this. So basically, the idea is that we have 3 cars here. They're going to be represented by these squares or rectangles, I should say. So it's so hard to see. Car A is on top. This one is A. This is, and 25 meters per second and accelerating at 1.5 meters per second squared. And we have B and C, labeling it far away to give myself room to write it squared. So here we have the velocity, it's moving down, but it's decelerating, so we draw the acceleration going up against the velocity. And decelerating 2 meters per second squared. This way. This one's getting faster, and these 2 are getting slower. And we know that the radius P is equal. Yep. Once we have everything written down, which we do, we can begin trying to figure out the question, which is determine the velocity and acceleration of car B relative to car C. So we're looking for B relative to C in both velocity. VB is equal to VC plus VB relative to C. just like we've been doing the whole time. Applies to both rigid body and particle kinematics, this kind of setup. So we know that the velocity at B is 15 meters per second. So we can demonstrate that like this. And we know that this angle is 30. So we can represent, so we need to find basically an angle to work with here. This angle would be ideal angle, and this angle have to be the same. It's probably difficult to see because I wrote 60 degrees. Because you can draw a horizontal line and then do alternate interior angles and then 90 minus this one to get the angle that we care about. Have the first velocity, this is going to be equal to VC. Velocity of C is 30 meters per second going down. And then we have plus VBC, B relative to C, which we do not know. So we will represent it as VBCY. And VBCX. Yeah, and so similarly to before, we can go, it's going to be 15 cosine 60, because cosine would give us this portion. And that's equal to nothing from the 30. VB. So that comes out to be 7.5 meters per second to the right. Then we do the same thing for y direction. We'll have 15 sine 60 degrees equal to minus 30 plus, so VBCY comes out to be 17 meters per second up. So do that as a magnitude, and we can get where this comes out to be 18.6. And then, like we did before, so we say tangent of theta, the unknown theta, is equal to our, we have the x component going to the right. So I'll draw this over here. We have our x component going right and our y component going up. So our velocity looks something like this. Here's our theta. So our opposite is going to be y, our adjacent is going to be x. So we'll have tangent theta is equal to 17 meters per second over 7.5 meters per second. Solve this for theta. We get theta is 66.2 degrees. So your answer for the velocity of B relative to C, you would say B relative to C is equal to 18.6 meter per second at 66 point. AB is equal to AC plus AB relative to C. So we'll bring this down. And say that R is squared tangentially also an AN here. It's moving in to your path. Because in order for the car to turn, there has to be an AN. So we know the AN, or you can just write this as R. So we have our velocity of B. Right, or wait, we have the velocity of B right here. And we know the R value is 100 meters. The way the curve is drawn, it has to be moving to the left. So that's why I draw. I can't even. 2.25 meters per second squared. This is equal to the acceleration at C, meter per second squared, and the unknown acceleration of BC. We do this, plot our components as an unknown coordinate, and we say sum of the forces X is equal to X components of both of these, which we know from before that this is 30 degrees, 60 degrees, and 30 degrees. And then if you want, I can go after the problem and explain how I got these angles, because some people get confused on these. So we have our X components for these. So that would be 2 meters per second squared times sine 30. We use sine here because of the position of, and then we'll use, this would also be negative because it's pointing to the left, plus 2.25 meters per second squared times sine of 60 degrees. And that's going to be equal to nothing here because this is perfectly vertical, equal to our unknown A, B, C, X, which meter per second squared to the right. Because we get a positive answer. So our assumed direction is correct. Then, yeah, so we found our ABCX, then we can do our sum of the forces Y. Take our Y components of this. So that's going to be 2 meters per second squared times the cosine of 30 degrees. We use cosine because 2.25 meter per second squared times cosine 60 degrees. And this is all equal to plus 3 meters per second squared plus the unknown ABCY. So ABCY is again our only unknown, and we can solve all of this and say ABCY comes out to be 0.1429 meters per second squared. Because we end up getting a negative answer once we subtract the 3 over all of this minus the 3 meters per second. So our assumed direction of up is incorrect. So then finally, we find the total acceleration like we did before by doing the square root them, and the answer comes out to be 0.959.
How do you get 0.14?
Hmm?
How do you get 0.14? How do you go from 3 plus? ABY.
It's so your final answer for the acceleration of B relative to C would be 0.959 meters per second squared at 8.57 degrees.